This meeting is being recorded.
Okay, good afternoon, everyone. Today we'll continue where we left off again. So on Monday we introduced the idea of accumulators as an additional argument to keep track of some things as we progress through a recursive data structure. Right. The initial motivation that we use for accumulators was actually to be able to implement a pathfinder between two nodes in a graph. Right. There we needed an accumulator as to keep track of the nodes that we've seen so far. So we needed a list of things that we already explored so that we don't end up in cycles and don't end up just chasing our tail as we progress through a graph, right? So there it was driven by a need to somehow be able to be able to even terminate on certain graphs. So that was kind of the motivation for graphs. But accumulators are a more general idea and a more useful idea than just for graphs. The way we used it in our next example was actually to improve performance of a function, right? The example that we used was to calculate, to take a list of relative distances between different points, and to calculate the list of absolute distances that we have to travel as we go from point A to B to C to D, etc., ending with a final distance. Our initial implementation using the list template basically relied on a list abstraction on map to, at each step, update the complete list with any new distance that we are processing, right? So we were basically going from the back and calculating the absolute distance as we are adding new distances to the front of the list, right? And we established that this is quite a wasteful way to implement this function, because at every point we not only were going through the list, but at every point any list that we already constructed in the recursive call, we reprocessed again and again, adding the new relative distance to everything that was in the list already, right? And then we kind of realized that, well, what if we would go through the list once and we would just keep track of the distance that we traveled so far, right? Because what we are really doing here, if we have a list of relative distances, we start with 0 as the distance traveled so far, right? We didn't travel anything. Once we travel a relative distance of 5, then that means that we traveled 5 so far. So the distance between the first point and the second point is 5. If we travel another 1 mile, that means the total distance is 6. If we travel another 6 miles, the total distance is 12. To travel another 9 miles, the total distance is 21. So just by using an accumulator to represent the distance traveled so far, we can avoid going through the list and again, because we keep the information that we need at hand when we need it, instead of recalculating it for each new element. And we kind of extracted or summarized the steps that we go through whenever we want to introduce an accumulator or use an accumulator for a computation into these kind of 4 steps, right? The first thing that we need to do is, if we are using some sort of accumulator, decide what it needs to describe or to represent. Sometimes we immediately know, okay, I need to keep track of the nodes that I visited so far, so actually that drives you to use an accumulator, and then you realize, oh, I'm using an accumulator here. So we first kind of give it a role, describe what it represents, and that kind of that guides you towards the rest of the steps. You need to decide what the initial state of an accumulator is, right? If I keep track of the nodes that I visited so far, initially that must be empty, because that makes sense with what it represents. If I use it to keep track of the distance that I traveled so far, initially that must be 0, because I didn't travel anything. So once I decide that, then I need to decide how each step in the processing of the recursive structure modifies the accumulator. What do I do with each additional information that I have, right? Where in graphs, we just pop the node that we just saw right onto the list of nodes that were visited, so that we remember, okay, we've been here, we don't need to revisit, kind of keeping the light on as we visited it. For the rel abs function, we updating or each recursive calls means that we update the absolute distance that we traveled so far. And finally, once we know how to update it, we need to, of course, exploit it in some way, right? If I just accumulate the distance, that doesn't really help me. I actually want to use it somewhere. So that's a kind of recap where we got to. And today we'll do a few more examples of accumulators and using accumulators. We'll do the first example that we'll do, and I think I mentioned at the end of the lecture to ask you to think about it, is writing a function to reverse a list. Right? So the first example that I want to look at and see how we can exploit an accumulator is in writing design a function to given list, and we'll implement it both using the usual list template as well as an accumulator-based design. So we want a reverse function that takes in a list of some elements and returns a list of the same type of elements. We want it to be generic. We'll use a list that is list. Some examples. If I have the empty list, of course the reverse of an empty list is the empty list. Another simple example is if I have a list of one element, then Reverse of a list of one element is again the same list. Slightly interesting, and also to change the types around. If I have a list of multiple elements, then I want a list that contains the elements in reverse. Right? It's relatively clear. Let me write a stub for this function using a list template, empty something. If it's cons, then we have a first element, and we have a rest of the list, and we want to do something with the rest of the list. Okay, let's get rid of the simple case. If I have an empty list, what do I return? Yeah, just an empty list. It's given by the example there. In the recursive case, I have an element from the front of the list, and I call reverse recursively on the rest of the list. What do I do with these two things? Josh? So I cons like this? Yeah, this wouldn't quite work. What would it produce? Yeah? Just the original list. We are not flipping the order. We are taking the first element, leaving it in the front, processing the rest, which does exactly the same thing, and we don't do anything. What do I need to do with the first one and the second one? Cons the rest of the list with the first of the list. So I'll go from that one. So that's an idea to take the rest of the list and put it actually in the front of the first element. But of course this won't work with our types. So what we need to do instead is to use append and give it a list to append to. Right? We take the first element, create a list out of it, reverse the rest of the list, and append the last element, the singleton list containing the last element, to the end of the reversed thing. Right? Make sense? Easy peasy. Okay, we seem to work. We seem to have a good reverse function. What is annoying about this function? Josh? I think yes, if I understand correctly what you mean. It has exactly the same performance characteristic as Rev Apps, right? At every point, append needs to go through the whole of the first list to append anything to it, right? It goes down the list, keeping the elements in the front until it reaches empty, and then it appends the second list to the first list, right? So let me just do this step by step and see how this actually behaves. So that we see kind of like how many appends we deal with there. So because this list is an empty, we have the cons case. That means that we append the reverse of the list containing B, C, and D to the list containing just A. So we append ref list B, C, D to a list containing A. Right? So that's the first step. In the next step, we do one more append inside here, in which we move the list B to the end. In here, append, take C, append it to the end. Finally, append the reverse of an empty list to a list containing just D. Right? So what we end up with at the very end is just a chain of appends, right? Where each append has to go through whatever the first list completely to be able to append just a single element to the end, which is kind of annoying. So the first append is really simple, returns immediately, just returns list containing D. The second append has to put D aside, append the list containing C, and return that list. So we take the list apart, reassemble a list of 2 elements. Then the next append has to again take the list apart and reassemble a list of 3 elements. The next append has to take the list apart, go through each element, append D, and reassemble a list of 4 elements, right? So we again have the same kind of performance characteristic, where at each step we go through whatever we already processed through the whole thing, okay? Which seems wasteful. So let's try to use an accumulator to avoid this waste of time and waste of resources, right? When we compute. The idea of using an accumulator with reverse is kind of simple, right? What we accumulate is a list or a version or a list that contains all the elements that we've seen so far in reverse order, right? We start with A, take A, the reverse of just A is just A, right? Then we get to B, we have a list that's reversed so far, so what we need is we saw A and B, and the reverse of A and B is B and A, so we add B to the front actually, and we get the reverse of the list so far. When we get to C, again we have B and A, so all we need to do is to put C in front of B and A, and we get a reverse of the elements that we saw so far. Finally, we get D, we have the reverse, we add D to the front, and when we are empty, we have now already a list that is in reverse. So let me write a version 2 of my reverse. As before, we kind of want to keep the same signature. We want the function to look the same to the outside world. So we hide the accumulator helper inside of the function. Fine. Helper, taking a list. And as I said, the accumulator now will represent the don't need this many letters of the elements that we've seen so far in reverse order. Right? helper takes in a list of X. The accumulator happens to be exactly of the same type now, of X, and will return a list of X. Okay. Now the next step in a kind of accumulator recipe or guidelines was to decide how do we kick off the computation using an accumulator function. Give it the same list before we get into the helper, before we process any elements. The list reversed so far, the list of elements seen so far in reverse is of course empty, right? So there's nothing to do there. And we use our list template to complete this helper. OX, something for the accumulator. We have a stop, so yes, local define. Okay, so we know what the accumulator represents, we know what the initial state is. Now we need to define what do we do with it at each step. And we established that what we do is actually take whatever we've seen that was in reverse, right? Always assuming that reverse so far contains is a list of elements that we've seen so far in reverse order. And to preserve that property, we simply need to add the first element to the front of the accumulator. And okay. Anything else to do in this case? Josh? Good question. So we assume, our assumption that we are working, or why this function will work, is that our accumulator contains, at each point, as we are in the list, at each point the accumulator contains the elements that we've seen so far in reverse order, right? So the front of the list is the most recent element that we processed in the list, right? That's before we enter this function. Once we get our first element, the most recent element that we've seen is the first element from the list. So that's why I put it in there. Okay, and then thus we preserve the property of at each point. So when we process A and B, then reverse so far needs to contain those elements in reverse. So it needs to contain B and A. Once we see C, to preserve that property, it needs to go to the front. Okay. And once we did that, actually for this function, there's nothing else to do with the first element. So we can just get rid of this. And we're good. And finally, to actually use the accumulator to exploit it, right? Once we get to the empty case, again, we assume, or we hold on to the property that this contains the list of elements that we processed in reverse order. When we are in the empty case, that means that all the elements that came before are now in reverse order in that list. So all we need to really do is to return the accumulator, and we're done. Right? Let me copy the test cases. Check that we are still good. And we are. Okay. I'll quickly do a step through of what Rev Helper does. So let me take this one like before and process it step by step. So Rev v2 just calls Rev Helper with LOX and empty, where LOX is list A, B, C, and D, and empty. In the next call, first is A, right? We are in the cons case. So what we do in the next case is call Rev Helper, where we take the rest of the list, which will just be B, C, D, and the list where we put A into the front of the empty list. So what we get is this one. All right. And then it kind of proceeds in a boring manner, where we simply just take the first element of the given list and put it at the end of the at the front of the accumulator. And finally, we have an empty one. Right, so this is the empty case. At the end, we actually have the reverse list in our accumulator, so we just return that one and we are done. Okay. The way to think about it is really like when I have a stack of cards, right, and I want to have them in reverse order. The kind of slow and boring way to do it is to take one card at a time and put them onto the table, right? And if I do this one by one, in the end, I get the same stack of cards. They're just in reverse order. Okay, so, and of course, the thing to observe here is, whereas at each step in our original reverse, we kind of, what we accumulated was just a little bit of that, right? Because we still needed to append all those lists together. At each step here, we don't have any operation to do. What we needed to do, we already did. We just put the element onto here. And because cons is a simple function, right? It doesn't have to go through the list. You just take an element and put it into the front of the list. It's just linear in the number of elements here. Okay. And just to point out, we cannot do any better than this unless we do use an accumulator, because we need to put it at the end of the list. With the way that our lists are, putting something at the end of the list means going through the whole list, finding that empty case, and putting that element there. So really always will have that performance. Okay, any questions? Okay, now let's do another function that we originally did, and we actually used Foldar to define it later on. Let me define again a sum function which sums up a list of numbers. So the way we wrote it using our list template was, if we have an empty list, we return 0. If we have a non-empty list, we take the first element and add it to the sum of the rest of the list. Okay. Here we don't really need to use an accumulator. We don't get any performance benefits, except one. So because the way we do this, just like with the append, to actually compute the sum, we need to go through the whole list before we can sum up all the numbers, right? An alternative way to define this using an accumulator is to define a helper which goes through a list and accumulates the running sum of all the elements that we've seen so far. Right? So, or I can also call it sum so far. Okay. Then running the sum would amount to running the helper with the list of numbers and giving it 0 as the sum so far, or the initial running sum. Now again, we just use the list template. Empty cons So similar to the reverse function, what we do here is we simply take assuming that this is the sum of all the elements that we've seen so far, that is the running sum, we just take the first element and add it to the running sum and hold on to it. All right, so we update the accumulator with the sum of numbers that we've seen so far, and at this point we are done with the element there. And that's all we need to do in the recursive case. What did we? We'll get to that. It actually is in some cases. Okay. And now when we are done, again, we have the assumption that sum so far contains the sum of all the elements that we've seen so far. So at this point, all we need to do is to return that one. Okay. Now this is jumping ahead, but since folks ask about it, the difference between these two versions is that in this case, at every step, we kind of need to hold on to the element that we've seen because we still need to compute the sum of the rest of the list, right? So even after we've gone through the rest of the list, then what Racket needs to do now, it needs to add all the elements together, right? And this is beyond the scope of this course, but this means that this version of the function will use more memory because somewhere there needs to be a record of this. This is still something that needs to be done, right? Because the result of the recursive call is an argument to another operation. In this case, once we see the first element, right, we can add it to the sum so far, and we can forget about it. It's gone, right? We just go down the list, and once we are done, we have the sum, we just return it. So nowhere during the execution, there needs to be some sort of trace remembering, oh, I still need to add all these elements together. It's performed right here. And again, outside of the scope of this course, but a good motivation, the difference between these two functions is that the recursive call here is in what we call a tail position. You don't wait for the recursive call to return the result and then combine it with something else, still process it. The result is the recursive call itself. Here it's not in the tail position. The last thing to be performed in this function is to add the results. Okay, so this is much more efficient, and many languages will allow to generate a more efficient code out of this. Okay, but as I said, that's beyond the scope of this course, but a good motivation to when you want to use accumulators, even for things like sum, where you don't really get such a tangible performance advantage as with reverse. Okay. But my motivation for doing a sum and using an accumulator right after reverse is to kind of observe the similarity between the two helpers that we introduced in these functions, right? So let me take them outside as global definitions and put them next to each other. And what I kind of want to do quickly is a little spot the difference game, right? Because there is a useful abstraction coming out of this. So in each case, if you notice these two functions, what we are doing here in the base case, right, in the empty case, we are just returning the accumulator. Right, so we might need some accumulator, and let me just do this. So here we are returning an accumulator, right? Then we have a recursive call to our function, which is right there in each of these positions, which we have a list here and a list here, a list of x. Call it on list of x with some accumulator. And okay. And let me just get this out of the way so that... What is the last thing that they differ in? Josh? Exactly. We apply different operation. Here we apply cons, here we apply plus, right? So what they differ in is that when we do have a recursive call, right, we apply an operation and we update our accumulator using that operation. Right? Does this function remind you of something? Josh? Foldar, exactly. Except we are not doing a right fold, right? We are not applying the operations in front just like in the original sum. We are applying the operation inside of the argument. Here we were just propagating base because we were waiting till the end of the list so that we can replace the empty with a base and recombine it with an operation. So this is like a accumulator version of foldar, but the consequence of this is that what we are doing is a fold from the left. Right? So this function really is fold_L, and I will name it my fold_L because fold_L is predefined. And let's also do the signature, right? So we need a type for the list of elements, we need a type for the result, right? The first thing for foldar was the operation that combines each element with what we accumulated so far and returns that. Then we have the base case. In this case, we just simply called it the accumulator. And then we have a list of X, and we return this, right? Which is exactly the type of foldar, right? But what it differs in is how we apply and accumulate the results. And now I can, of course, define a third version of reverse and a third version of sum using my abstraction. So what are the arguments to fold_L here? Exactly. Right. List of X. For this one, yeah. Exactly. Plus 0 and LON. Let me at least convince myself on reverse. So this seems to work. Okay. So the abstraction of not all accumulator functions, of course, but many of them is really left folding from the left. Instead of applying the operation on the outside and waiting for all the intermediate results to return and then combining it, we combine as we go through the list, right? Now, my question is, can foldar and fold_L be used interchangeably? So do my fold L plus 0 6 and can they be used interchangeably in this case? Josh? Uh-huh. So type-wise, it would be okay. Cons would still get the right arguments, right? Because it still obeys the signature. However, if let's actually do that. If I do cons, my fold L cons empty list 1, 2, 3, 4, 5, right? What I get back is the reverse of the list, which is just what we wanted in this case. Now if I use fold R, what do I get back? Yeah? Exactly, I get the same list, right? Because what we do is cons 1 with the result of consing 2 with the result of consing 3, etc. So we are just like rebuilding the list as we go along. Here as we go, we basically cons 1 to empty, cons 2 to 1 and empty, cons 3 to 2, 1 and empty, cons 4 to 3 to 1 and empty, etc. So the order matters there, right? So let me just write this out. First this one. So what happens here is this. 4 plus 5 plus 6 and the base case, which is 0. Whereas here we start with adding the base case to that. Then we add 2 onto that. Then we add 3 onto that. 4, 5, and 6. So we do everything in reverse order. Josh? Yes, so we need commutativity. Actually, no. The operation, it doesn't need to be commutative, right? Because cons isn't commutative. Because it has different types. You cannot just replace those things. Does it make sense? You cannot cons list to a single element. So the commutativity isn't there, but it's a good intuition. What actually matters is associativity, right? We kind of play around with commutative functions here just because the type of fold L and fold R are the same. So the order of the arguments needs to be in the same order. But I could have rewritten this part just as well as etc. Right? And there I'm associating to the left with fold L instead of to the right with fold R. Okay? But don't think too hard about it. So for now, the important property is associativity, but we can use them interchangeably also if they are commutative, and the order doesn't really matter. Where we do need to be careful about this thing is if we use the same thing. Let me do this, and we use minus, for example, right? Where using fold R will give us a different result than using fold arrow. And not only because minus is not commutative, but it's also not associative, right? The order in which you subtract things matters. And this should be all minuses, so does not really work. Okay. Any questions? Yeah.
Why do we define a separate fold-out?
Sorry.
Like, could we have just used regular fold-out?
Yeah. It's exactly the same.
Yeah, I was wondering. I was like, could we not?
No. So it's just to go through the exercise of actually like, well, there is a pattern for many of these accumulator-based functions, and that pattern can be abstracted in fold-L. Fold-L is just as fold-R provided for you, and its definition is basically the same. Any other questions? Okay, I want to do one more example with fold-L, and we are more of it done. So let me do this example. So imagine some sort of competition where the winner is determined using the following, right? You have a list of people who finished the competition.
Could you explain again how folded minus returns a positive?
Yeah, okay, actually. Since we have some time, we can do this. But you need to help me with math today because I'm really bad. If it's bad on normal days, then it's bad, particularly bad today. So we have the same thing. You can see I'm not very friendly with an editor if I replace everything manually instead of using search and replace, which I would do in my usual. Okay, so if we first start with fold-L, right? The order in which these operations are applied is exactly this one, right? So the first thing that we do as we go here, the base case is or the accumulator, the initial accumulator in this case is 0. So what we do is we subtract 0 from 1, right? And we get 1. Right? In the next step, we subtract the accumulator, so 1 from 2, and we get 1. In the next step, we subtract 1 from 3, so the accumulator from the next element, and we get 2. Subtracting the accumulator from 4, we get 2. Subtracting the accumulator from 5, we get 3. Subtracting the accumulator from 6, we get 3, right? And we get a positive 3. Now with fold-R, where we use the 0 as basically the base case, what we do is we subtract 1 from the result of subtracting 2, from the result of subtracting 3, etc. Finally, from the result of subtracting 6 from 0. So we go from the right, because we have the right fold. So we subtract 0 from 6, we get 6. We subtract 5 from, we subtract 6 from 5, we get -1. And we subtract -1 from 4, meaning we get 5. Please check my math. subtracting, what did I say we get? 5? Yeah, subtracting 5 from 3, we get -2. Subtracting 2 from -2, we get 4, right? Yes? Subtracting 4 from 1, we get -3, finally. Right? Gosh. So in this case, we get, what did we get? 3. And in this case, we get -3. Now, if the list had an odd number of elements, we would actually get the same result. Because funnily, with foldr, we are kind of flipping the sign at every step. So they would be the same. Okay. So that's why we get a negative number with foldr, but a positive number with foldl. Okay. It's best to like take, you know, some left and right folds, load it up in the stepper, and step through the execution. I will actually just take this and do the kind of what they correspond to. So foldr, if we get a function and base, and let's say a list of a cons b cons c and empty. Right, if you remember from when we did this, what this really does is replace every cons with an application of f in the same order, and replaces empty with the base. So that's how foldr behaves. On foldl, on the other hand, if I use base for the name, e cons c empty, and let me do this stepwise. So what we do is replace base with f of a base as we removed each element. Then the next one, next one, all right, and finally what we get back is just this. Okay, so there we kind of just to illustrate the difference schematically. Okay, so final example. So where was I? So let's say that I have a little competition, and the winner of the competition is determined based on the following two things. The person who achieved the highest score in the competition, but also the first person who achieved the highest score out of all of these people, right? So let's say that I have a representation for a score where I have a name and the number of points, right? A score is make score name and the number number of points. Right? And I want to write a function called winner, which takes a list of scores and returns the winner. So a name with the point count, and assuming that the list is ordered in the order in which the people finished, right? So the first person to finish is the first person of the list. The last person to finish is the last person of the list. Let's do an example. Let's do, I don't know. Okay, so we have a list of scores. We have two people who hit the maximum number of points, right? Who have a highest score count. However, only one of them finished first. So what we really want from here, let me add one more potential winner so that it's a little more balanced. So what I want, effect of scores. So of course get back Lisa, right? Because of all the people who achieved the same score count, which was the highest, she is the one who finished first. List of scores. Okay. The way I can do this is, of course, if I have a comparison function which takes two scores and returns the one that is the highest one, right? So let me do a local definition for that. Max score, where max score will take a score and return the maximum score of those two. Score 2, and simply returns if score 1, if the points of score 1 are higher than the points score 2, then return score 1, otherwise return score 2. Pairwise comparison, give me the highest one. Now once I have a function like this, I can use foldal to give me the winner, right? And I need to give it some base case. So what I'll do is I'll simply say, okay, if somebody or if nobody achieves more than 0 points, there is no winner. And I give it the list of scores. All right, now if I run this, it works well. Because what in effect happens here, because I'm folding from the left, right? Foldal will give me a left biased maximum of the list. Right? If I used foldar in this case, right, I would also get a maximum, but I would get All right. I would get the last person who finished. Right? So when you deciding between foldel and foldar, it's like there's multiple things, but one of the things where you can think about is, does the order of the list matter, right? And do I want to process it from the left, or do I want to process it from the right? If the order doesn't matter, you can reach for foldar depending on the function that you are using. Does the order matter for the function? Otherwise, if I want to process from the left, I can use foldel, which also gives me a better performance characteristic. Okay, so that's roughly where you might want to choose one over the other. Are there any questions? Yes?
So if two things are equal, but you want priority of the one that comes first, you use foldel?
Yes. So for example, another example would be when we did the binary trees, right? And we use foldar to construct the binary search tree out of a list, right? The first element that was actually inserted into that one, because we use foldar, was the last element, right? So that was the top of the tree. If I wanted to do it in reverse and I actually want to go from the left, I could use foldel with exactly the same function, and the first element inserted would be the first element of the list, right? So if I want to start working from the left, right, like I process the list from the left in any case, because that's how we work with lists. But if I actually want to combine or start combining from the left, then I reach for foldel, because that starts, and it's quite often the more natural order when we look at lists, right? But it doesn't always work. So, yeah. Any other questions? Okay. I really recommend just loading up some examples, firing up the stepper, and kind of seeing how they behave, trying different functions, associated, non-associative, commutative, non-commutative, and kind of getting a feel for it. If there aren't any other questions, thanks so much for coming today and for joining online and for participating. I'll see you around tomorrow or in office hours. Thank you.